Hello and welcome back. We've been talking about reactions on a benzene ring. This is video number 5 and it's part A. You'll need to get through all 3 parts in order to be able to work all of these problems from the chapter 18 problem set and to meet this learning objective. So let's go ahead and get started. We've been talking about reactions on a benzene ring, and you have access to this handout as well as one other, and it'll be useful also to reference your assignment for this week. So let's go ahead and get started. So remember in the previous unit I mentioned that nitrobenzene is much less reactive than benzene, and I said you'll need to memorize for now that a nitro group is a deactivating group, but in the next unit you'll learn why and be able to explain why it's a deactivating group. So that's what we're going to do. So when we have something on a benzene ring, a group or a substituent, if it is able to push electron density into the ring, so I'm put here a partial negative charge, it'll make the ring more nucleophilic. And so we expect it to be more reactive to this type of reaction here. Remember, this was an electrophilic aromatic substitution reaction. The electrophile here is that nitronium ion, right? There's our nitronium ion, okay? So if we push electron density into the ring, remember that is, the benzene ring is serving as the nucleophile to attack the electrophile. So the more electron density we push in, the more activating that group is. Now, the more the substituent or the group on the benzene ring withdraws electron density from the ring, then it makes the ring less nucleophilic, then that group is classified as a deactivator. So this is a partial positive charge here that I've put in the ring, because whatever D is, it's withdrawing electron density from the ring. So something you'll need to be able to do on the next exam is I'm going to give you a group, let's say it's like a nitro group, and you'll have to be able to tell me, is it an activator or a deactivator? And so to assess that, there are 2 things you have to consider. You have to consider the inductive effect and the resonance effect. Now, usually resonance is the winner, but as we'll see with the halogens, not always. So let's compare each of these effects, inductive effect and resonance effect, one by one. So first of all, what is the inductive effect? So inductive effects occur through sigma bonds. So remember that a single bond is a sigma bond. It's also helpful to remember your electronegativity trends when assessing inductive effects. So if you have an electron withdrawing group, something like a halogen that's attached to a benzene ring, here are other examples of substances that are each electron withdrawing. They're going to inductively withdraw electron density from the ring. Okay, so all of these are electron withdrawing from an inductive standpoint. What can be electron donating? Well, an alkyl group is going to be electron donating, okay, via induction. So if you have something like a methyl group, like if this was toluene, that is going to inductively push electron density into the ring, making this more electron rich, and then a better nucleophile. Okay. Now let's take a look at resonance effects. So here toluene is electron donating inductively. Now there's no resonance effect for an alkyl group because it can't, notice I can draw resonance for this just moving these electrons around in the ring, but I can't move any electrons from the alkyl group, right? Because they're all single bonds and there are no lone pairs. So It's really important to recognize that if you have an alkyl group bonded to a benzene ring, it's only the inductive effect that's going to determine that it's activating, right? So if something is electron donating, like an alkyl group is, and it has no resonance effect, then it's the inductive effect here that's going to say that this is going to serve as an activator. Now let's look at examples from up here that where we have to consider the resonance effect. So resonance effects occur not through sigma bonds, but through pi bonds. So if you see a double bond or a triple bond, usually resonance effects win out or are more important than inductive effects. Halogens are the exceptions. So if you have electrons that are going to be electron density that flows into the ring from the substituent via a pi bond, then you're making the ring more nucleophilic, and that group is going to be an activator. If, on the other hand, you have electron density flowing out of the ring through sigma bonds, then you're making the ring less nucleophilic, and the group is going to be a deactivator. Okay. All right, so you have to consider both inductive effects and resonance effects. When they're in agreement with each other, it's easy. So if they're both going to be electron donating, so they're both activating, or if they're both electron withdrawing, deactivating. But when they're not in agreement, usually resonance wins. You have to know that halogens are the exception to that. So let's take a look at how to assess resonance effects. So let's take phenol. So here we have phenol, and we said from an inductive standpoint, it was electron withdrawing. So we think of it as deactivating, but from a resonance standpoint, it's not. So I can take the lone pair from the oxygen, push it down here, and then I'm going to take this pi bond and make it into a lone pair. So as soon as I draw this resonance hybrid, I see a formal negative charge in the ring. So I know from a resonance standpoint that OH group from phenol is going to be electron donating, making the ring more nucleophilic. Okay, and I can draw other resonance hybrids where I again see a negative charge in the ring. So that tells me from a resonance standpoint, the OH group is electron donating, so an activator. This is in opposition to what we saw from the inductive effect, but again, the resonance effect is going to win out here. So I'm going to go ahead and say resonance effect is more important here than the inductive effect. And this is true for everybody except the halogens. Okay. All right. So now what we're going to do is we're going to compare the nitration of benzene to that of toluene. So toluene reacts much faster than benzene towards nitration. So here's the nitration of benzene. Here's the nitration of toluene. And here's the ortho product. You can draw the meta and the para. What we find experimentally, so you don't need to memorize these numbers. The regiochemical outcome of the nitration of toluene is that we get ortho and para as the major products. We get very, very little meta. So now we want to explain why toluene is an ortho-para director. So we know this is an activator via the inductive effect. Remember, the alkyl groups have no resonance effect. But why is it that it's an ortho-para director? Meaning we're directing the nitro group here to the ortho and the para positions. So that's what we want to be able to answer now. So let's do that. So I did this in class, but I'll go ahead and walk you through it again. So if I draw out the rhenium ion intermediate that we get for ortho attack, meta attack, and para attack. I'm going to see, is there a resonance hybrid that's especially stabilized or especially destabilized? And I've gone ahead and highlighted for you here that in the ortho and then in the para, we have a resonance hybrid where the plus charge is on a tertiary carbon. Okay? So that's especially stabilized. So that means that the transition state leading to the ortho rhenium ion intermediate and the para rhenium ion intermediate is stabilized, lower in energy relative to that for the meta rhenium ion. Because here, remember, this is all secondary, 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 right? Okay, so if I look at the reaction energy diagram, the meta transition state leading to the sigma complex or rhenium ion via meta attack, this transition state is much higher in energy than that of the ortho and the para. Okay, and you don't have to worry about deciding if the para versus the ortho is higher than the other. Okay, they're going to be very close in energy to each other. And honestly, in most of the time, once we have something bigger than, if we have an activator that's bigger than 2 atoms, like we see with the phenol, normally this is what we normally see. Okay, but again, what you have to recognize here is that the transition states leading to the ortho and the para intermediates and then their products is stabilized relative to that of the meta. Okay, so this ortho-para direction as the alkyl group is an ortho-para director, and activators are ortho-para directors. Okay, so it's largely determined by the group's ability to stabilize that transition state leading to the rhenium ion or the sigma complex intermediate. Okay, all right. So what I'm going to have you do now on your own, and this was part of your assignment, is to take a look at the nitration of anisole, which is methoxybenzene. So this is the group, and it has 2 lone pairs on that oxygen. From an inductive standpoint, because of that oxygen, it's electron withdrawing, so we expect it to be deactivating. But from a resonance standpoint, right, I can bump this pair of electrons down, and then I get a negative charge in the ring. It's electron donating, so it's activating from that perspective. So I'm going to let you go ahead and fill this out. I think on your handout, I think it switches these 2 around. You may have to relabel it if you screw it up like I did. But I want you to practice this using anisole. Okay, and what you're going to find, what you should be able to explain is why we end up seeing these 2 over this one. So something for you to start burning into your brain is that all activators are ortho-para directors. Okay, so we're going to pick up here in video number 5, part B.